Hello, Professor. Hello, everyone. I'm Chen Hong-Guang, a first-year master's student in the Artificial Intelligence degree program. Student ID 314505009. My topic today, Dataflow, memory hierarchy, and compile-time determinism. The three architectural trade-offs that define heterogeneous AI accelerators in the LLM inference era. So why this topic? Here's the thing. In Professor Liang's IEEE paper, he points out a key insight. In LLM inference, the context phase is compute-bound, but the generation phase is memory-bound. This means no single general-purpose accelerator can be optimal for both. So instead of going broad, I'm going deep. I picked three battle-tested paradigms, Google TPU, Groq LPU, and NVIDIA Blackwell, and I'll analyze them along three axes. Let's dive in. Here's the roadmap of this entire talk. A 3x3 matrix. Vertical axis, three paradigms. TPU goes fixed systolic array. Groq does software-defined tensor streaming. NVIDIA stays with the SKMT plus tensor core hybrid. Horizontal axis, three analytical axes. Axis 1, Dataflow Philosophy. Axis 2, memory hierarchy. Axis 3, compile-time determinism. And the bottom line is this. Divergence here isn't about who's stronger. It's about who placed the right bet on a specific LLM inference workload. I'll fill in this matrix cell by cell in the next 6 slides. Axis 1, Dataflow Philosophy. In 2016, Eyeriss classified Dataflow into 4 categories: WS, OS, RS, and NLR. Let me tell you where each paradigm lands. TPU is the weight stationary champion. 65,000 max in a 256 by 256 systolic array. Only 5 CISC instructions. Control logic, less than 2% of the chip area. That's extreme minimalism. GPU lands in the NLR or IS region, relying on L1 and L2 cache for dynamic reuse. Very flexible, but utilization suffers. But here's the most interesting part. Groq doesn't fit any of the 4 Eyeriss categories. Their functional slicing invents a brand new category, Spatial Pipeline Dataflow. 20 super lanes, east-west hemispheres, and the compiler nails down direction and timing for every stream. So the takeaway, TPU inherits the classics. NVIDIA stays general. Groq invents something new. Axis 2, memory hierarchy. This is the most dramatic slide of the talk. Start with TPU Ironwood. HBM 3E, 192 gigabytes, 7.37 terabytes per second, plus 3D Torus and OCS optical switching. Now look at TPU 8i, the inference-specific SKU. On-chip SRAM tripled to 384 megabytes. Ici doubled. And Google says it explicitly. This is for MoE workloads. Groq is the extreme case. SRAM only. No HBM, no DRAM. From TSP's 20 megabytes to LP30's 500 megabytes. On-chip bandwidth, 80 terabytes per second. That's 24 times of H100's HBM bandwidth. But there's a cost. Running Llama 370B requires 576 LPU chips. Hardware cost, 40 times that of H100. Now the most surprising move, Rubin CPX. NVIDIA actually launched a chip using GDDR7 instead of HBM. Why? Because during prefill, HBM utilization is only single to double-digit %. That's pure waste. GDDR7 saves over 50% cost and 90 cents per GPU hour. So my view, NVIDIA themselves are proving that not every inference stage needs HBM. This is partial vindication of Groq's path. Axis 3, compile-time determinism. This is Groq's most radical bet. TPU uses XLA AOD graph compilation. NVIDIA uses CUDA with dynamic warp scheduling. But Groq goes all in on static. Let me quote Professor Liang's A5 slide 7. Software essentially orchestrates all the data flow and timings. No stalls. No sincronización o overhead. Latency completely predictable. How predictable? Cross-chip plesiochronous link. Vector latency is deterministic down to 10 cycles. And the numbers prove it. On Llama 370B, Groq runs 284 tokens per second, while H100 does 60 to 100. On Mixtral, Groq beats GPU by 6 to 9 times. But here's my view. This bet only works if the LLM architecture converges. If Transformer stays stable, Groq wins. If new architectures like Mamba, SSM, or Diffusion take over, general purpose wins. Now my 2 personal views. Number 1. MoE breaks static compilation. A 5-step argument. Step 1. Groq assumes all execution paths are known at compile time. Step 2. But MoE token routing is decided at runtime. Step 3. These two are fundamentally in conflict. Step 4. Professor Liang himself raised this concern in A5 slide 5. Quote, Groq hasn't disclosed how long it takes to reconfigure for a different algorithm. Step 5. But Groq fights back, still 6 to 9 times faster on Mixtral. Hold on though, that's 6 to 9x is partly because GPUs are just bad at MoE, not because Groq solved the dynamic problem. Compare the 3 strategies. NVIDIA Blackwell has tensor memory plus expert parallelism, born from MoE. Google explicitly doubles ICI in TPU-8i, admitting that dense systolic isn't enough. Groq relies on compile-time expert preloading, but this already deviates from their zero overhead synchronization philosophy. The conclusion: Groq must choose between inference cost leadership or adaptability to new models. They can't have both. My second view: heterogeneous specialization has begun. General-purpose GPUs are being disaggregated. Hard evidence: 3 pieces. 1. NVIDIA Rubin CPX uses GDDR7 and PCIe Gen 6. They didn't even need NVLink, saving $8,000 per GPU. 2. Google's 8th generation TPU directly splits into 8T for training and 8I for inference. 3. Groq has been inference only from day one. 3 companies, independent decisions, converging on the same direction. Here's a historical analogy. CPU spawned GPU. GPU spawned NPU. And now the GPU itself is being broken apart. My prediction for 2027 to 2028. First, Prefill plus Decode dual-chip configurations become a standard. Second, an inference-specific memory hierarchy emerges. GDDR7 plus stacked SRAM plus selective HBM. Third, MoE-native interconnect topologies become mainstream. What does this mean for Taiwan? Don't chase the general-purpose GPU race. We lack the resources. Focus on heterogeneous packaging integration. What Professor Liang highlighted in A1 slide 9, HBM and CoWoS. That's our real opportunity. Conclusion: 3 axes, 3 short-term winners. NVIDIA wins on data flow flexibility. NVIDIA wins on memory capacity. Groq wins on compile time latency. But midterm, in 2027 to 2028, all 3 axes will go heterogeneous and hybrid. One-line takeaway: in the LLM inference era, accelerator divergence isn't fragmentation. It's division of labor. 3 paradigms, each owning a workload no one else can touch. And let me close with a callback to 1979, H.D. Kung's systolic array. Dataflow is a 1970s concept, but in the LLM inference era of 2026, it is being reborn in a new form. Thank you, and I welcome any questions. Appendix A: Eyeriss Dataflow taxonomy in more detail. Weight stationary minimizes weight read energy. TPU is the representative. Output stationary minimizes accumulation cost. Shurdianeo. No local reuse is the simplest but most energy-hungry, closest to GPU SGMT. Row stationary is Eyeriss's own contribution, 3-dimensional reuse with the best energy efficiency. And Groq's functional slicing doesn't fit any of these 4. It's a new spatial pipeline category. Appendix B: the roofline model. The core formula: attainable performance equals the minimum of peak flops and arithmetic intensity times peak memory bandwidth. For LLM Decode, arithmetic intensity is about 2 memory bound. For LLM Prefill, arithmetic intensity is order n compute bound. This directly explains Groq's all SRAM strategy and Rubin CPX's choice of GDDR7 over HBM. Appendix C: references. 9 academic papers covering Juppie's TPU work, Apps's Groq TSP papers, Williams's roofline model, Chen's Eyeriss, and Sharma's recent LLM accelerator survey. Plus 6 industry sources, Google blogs for semi-analysis deep dives and artificial analysis benchmark data. Appendix des courses réflexion. The 7-layer architecture model is the most valuable intellectual asset of this course. Layer 1's 12-point design checklist is essentially a complete map of AI accelerator design. My suggestions: add a roofline lab session, invite Taiwan's semiconductor industry guest speakers for Layer 1 and Layer 2 perspectives, and build a reading guide for semi-analysis and hot chips materials. Thank you, Professor Liang, for a really great semester.